from the different topics. So everything actually at the end we concern about the healthy, environmental, and energy. So water is a material fundamentally for environmental healthy and also for energy. So whether water is just a solvent or functional material, that is something probably we know, probably we don't know. And how to explore water as a functional material, and probably is a very important topic. That's the about science. That's my personal view of this topic. So we are how to spell for. So we are. So water is a research topic, but not everyone started research of water at the very beginning. So we are interested on polymer chemistry. We are interested to make a new polymer. The idea is to put the metal in polymer, to make a polymer have a metal function. That's a very good idea. Started many years ago, but progressed very slowly because additional organic polymers. It's interesting, but still challenging. And we're trying, but it's make a contribution to the self-assembly. We made a significant contribution in the self-assembly using special metal-containing polymers. At the end, we try to using self-assembly to produce nanomaterials. So we always the fundamental synthetic factor for nanomaterials probably in the future, self-assembly, but it's a long way to go. However, my research is theoretically driven. That lead me to interested in the role of water in the self-assembly. So that is interesting. It is painful because I lose my original goal. I come to the research of water, and I found it so interesting, and we should spend time on that, even another expert on that. So firstly is metal-containing polymers. The idea is put the metal into polymers. How to use this combine the organic metallic chemistry and the polymers. Organic metallic chemistry actually is based on the catalyst. It's not stable, certain degree of stable, but not stable. The idea is we put in, it's not really stable. But what we try to do is we can resolve this challenge by using host gas chemistry. Once we have host gas, we made it stable, and we are not stable thermodynamic. So it cannot be stable. So if we shine this polymer with light, the CO will be released. And CO is a very useful drug. So that actually overcome a challenge in the CO delivery chemistry. So that is quite interesting project in terms of final applications, long way to go. So we gradually lose interest of these because we not have to be I have to be honest with you, I'm not really expert on to push these to the final application. Another challenge is many of you probably working on the metal coalition polymer. Metal coalition polymer is some kind of material. At the first, people produce a few useless because they're not be able to process what it's going to be preceded once it's produced. Just recent year, people push it to function and interest. So we try to use in supramolecular chemistry to put the metal coalition on the periphery, then make this material processable. So they are suspended in water. Then after they can be recovered by adding some organic salt and you can recover. So it's kind of hollow structure could be quite useful. And the technique of the mid-emulsion peripheral formation can be used for different for real material application, not just for the metal coalition polymers. So metal coalition polymer is not at this stage. They are not very broad scope, just on the field. But they're very interesting in self-assembly. This is an example. This polymer is a crystallization properties. They can crystallize during the self-assembly. Then the end can serve as a nucleoside to induce the growth of the second block. In this term, we can design synthesis of block on the self-assembly. That's the first concept that organic block polymer self-assembly can be designed into nanostructures. So as metal coalition polymers, the one difficult challenge is that they are not stable. And so only very limited amount of main chain metal containing polymer exists. One reason is because organic metallic chemistry is not compatible with traditional polymerization technique. So that's why we think about can we using organic metallic reactions and use this reaction for the polymerization process. Then we can develop a new type of metal polymerization polymer. That's what we did. We just put this functional group into the one molecule. Then we undergo this repeated migration insertion reaction. We can get these polymers. And this polymer is stable as solid. And in solution, be stable over days, but cannot live a long time on the oxygen and on the air. So this polymer have many properties, but we know it's very difficult to compete with the organic polymers for their applications. But one thing they are quite interested in their self-assembly behavior. This is water insoluble, but they can self-assemble into stable colloids in water. And these colloids, we try to mix them with the using the calcium dye to examine the panascopic waste. So this is a self-quenched dye. That means they dispersed, they have a photofunctional. But if they aggregate together, they self-quench. So once we mix these colloids with this dye, and they still have some fluorescence, and TLC, and etc. But when we prepare these structures in the presence of this dye, all the fluorescence will speak. So that suggests, and also TLC, there's no dye. So that suggests that this dye will encapsulate the structure is kind of a hollow structure. And light scattering tells us is a kind of hollow structures. TEM is not very clear. It's a hollow structure. Probably the wall is very thick and containing this metal. We're not able to see it very clearly by TEM. Nevertheless, there's a lot of experiments we have done to show these have very special encapsulation properties. This could be very useful. Again, this is the material preparation is quite expensive. Compare with the many techniques to prepare the recipes. So the question, we are interested in why this water insoluble polymer can self-assemble in water to form stable structures. So this is actually not a very surprise for the biological model. Peptides can form stable structures, although they are very hydrophobic. The reason for that is that people pay attention to this. In this field, people actually start to research is the hydrophobic hydration. So what is hydrophobic hydration? Water can directly interact with your molecule to hydrate your molecule. Water can also interact themselves to form strong aggregated structures surrounding your hydrophobic molecule. That is kind of hydration and make your species stable in the solution. That is quite an interesting topic in the area. So water and H2O is different things. So they can be different structures, and the different structures have a different cohesion. So hydrophobic hydration is the water that has strong cohesion around your hydrophobic surface. So that cohesion could be changed by the different parameters. So that's why it's difficult by the molecular structure, by the molecular shape, and by the solution condition. There's one simulation. So this area research most powerful tool is the simulation. So there's one simulation indicator that this, if you have a charged species, hydrophobic cohesion around the labeling hydro can be enhanced. So that's the simulation. So we think about it based on this simulation. Based on this simulation, we think about it. Can we induce a charged group at the end of this polymer chain? So we can vary the charged species to their water solubilities from relatively a little bit of water soluble to very hydrophobic. Then what happens? Because for this simulation, you have a charged group, you can enhance the cohesion. Is if you have a relatively water soluble, they form iron pair. they going to hold the water structure between them. This leading to the backbone dehydration. That's very typical for the surfactants. That's very commonly we know about the surfactant behavior in water. But if they are hydrophobic, so this backbone stay hydrated. So they have a very different self-assembly behavior. So that is what we observe. So we vary the water solubility of this, and when this relatively water soluble, the colloids is a positive charge. That's because positive charge like surfactant they expose to the water. Hydrophobic, we got the best for structures. So this behavior is also conventional organic polymers. So for this polymer, they increase the water amount. So the background dehydrated. Then they form this helical structure. They form this because of hydration, influence of hydration, they form different self-assembly behavior. So polymer is too complicated to say. Think about block polymer self-assembly. Why we can develop this field? Because we have lots of knowledge about the synthetic things. More that knowledge we study develop a block polymer self-assembly. So that's why we think about we should study this small molecule. We think it's self-assembly. Probably because of this, and they do not have corona, because when you do NMR, there's only water signal, there's no corona, it's not surfactant. And their surface activities, their surface tension do not decrease. So that means they are not a surfactant, they are surfactant. So what's the reason for their self-assembly? We try to vary this hydrophobic, and this is not for our expectation is the longer the hydrophobic chain, the better the colloid stability. The shorter the chain, the swelling, and followed by little bit of precipitation we observed after several days. So what's the reason for that? Chemists, our core of research is design molecule. That is we are very proud of the chemistry. So what we do, we try to put this pyrite into this chain and try to using this fluorescence of pyrite to explore what happened in these structures. We found that it's formed vesicle again, and we found that there's no excitement. So in chemistry, probably we know is that if this molecule do not show excitement, means this molecule do not come together. That means that they are in the solution as colloids was separated by water. Water contributes to the stability. So we try to using the Raman analysis these colloids and found that this is the book water, this blue one. This red one is our colloids. We found that the water structure is different. And for this signal, it will be assigned to this tetrahedral argine. It's well-ordered water structures. And for this one is the common oak rock. They have different type of structures mixed together. And for this signal, it was well known is for the water interact with the aromatic group. So that signal tells us the structure is like this. The structure is stabilized by the ordered structures, and they also have a certain degree of interaction with the molecule. And so this bisulfite is a very interesting molecule. Bisulfite do not have a fluorescence because this bond is free rotating. That is dissipated. However, first from this structure, we have observed this broken vesicle, and from this broken vesicle we can measure its height, and from this height we can get some idea. The vesicle we got probably is kind of bilayer structures. And interesting is this molecule do not have fluorescence, But once we start to self-assembly, they start to form the fluorescence. So the reason probably because the liquid, the solvent restrict the rotation. This is free rotation fixed. Then the energy can be emitted by the line. So for the final product colloids, if we increase temperature, the fluorescence gradually decreases because increased temperature probably releases this kind of restriction and make this fluorescence become decreased. So similar is we can adjust this fluorescence by the mixed solvent, by the way of prepared, and by the line. So here, if we have prepared this vesicle, they have fluorescence. If we dialysis, so this portion the structure was a parallel pattern. So they don't have fluorescence problem. Probably is because they have a distance intermolecular conjugation. That's basically the energy. So we add water, they still have a low fluorescence. But in the presence of THF, and if we shine this vesicle with light, with UV, and we see the fluorescence, and this structure was from the torsional structures, then their intermolecular conjugation will disappear. And for the starting material, if we just bubbling, quickly remove THF, and this structure remains, and this will have fluorescence. We add THF, mix the solvent, and this structure still confined, and this still have a fluorescence. So by the end, it looks like we can using water to design its cohesive properties, then to control this molecular motion, then achieve this photoluminescence properties. So by the end, the research is just a start, and we need to continue research. So we have to think about what happened. So in water is a very dynamic it's kind of aqueous and very dynamically extended from different structures. So it's a form structures. It could be delta H unfavored, delta S favored if they destruct. If they assemble together, it is delta H favored, delta S unfavored. So overall, they contribute to the energy is delta G is 0. So that means the structural variation do not contribute to the self-assembly. So where the self-assembly occurs. So water is the self-assembly free energy for the self-assembly is from the water solute interaction. Is from water solute interaction, and it's so by the way, it's some kind of what I'm saying. 2 minutes, okay. So conventionally, we think about the water interact with the molecule through the hydrogen bonding, but we have to consider about the dispersion interaction. Dispersion interaction is also very important, and there's simulation stress on that. I'm not going to talk that too much. So summary is that we have synthesized the metal containing polymer with metal CO bond. That's very weak, and we can use it using supramolecular chemistry to make a concept of functional materials. And we can use supramolecular chemistry to make a metal crushing polymer become processable. So that could be in the future useful for some kind of applications. We also invented a new type of formation technique that created a metal containing polymer inserting formulation. By the end of this research, we developed our interest in water, and we think that water have a lot of potential to be explored. How to acting as a functional material. That is obvious in the biological material. That is going to be long way, I hope that people can get interested. Have to be depending on the collective research to develop this potential. Finally, thanks for your attention and thanks for the time.